Greetings, math fans. All right, this is day 3 of chapter 1. And the first thing we're going to talk about is more composite functions. And remember, math fans, we talked about this actually on day 1. All right? So let's just start out with an example here. Now, it was easy before. Before I just said what's like f of g of x and g of f of x. Pretty mellow, right? Okay, now I'm going to do, as an example, I can tell you f of x is equal to 2x minus 6. And I'm going to tell you f of g of x. Remember, that's another way to write it. Equals 6x minus 2. And my question is, what is g of x? Okay, it's a little more challenging now because now you actually have to say, what am I plugging into? Let me just write this out here. Question, what do you need to plug into x for f of x to get, what do you need to plug into x for f of x to get 6x minus 2. So I'm looking to see what I'm plugging into that value right there, math fans. Okay? Or actually, I'm sorry, what I'm plugging into this guy right here. What I'm plugging into that x. Alright, so that's actually pretty easy. So you're just saying 2 times g of x minus 6 is equal to 6x minus 2. That's all you're doing. Because, right, aren't you plugging g of x in there? So it's all, you're just saying 2 times g of x minus 6 equals 6x minus 2. That's actually pretty easy. I just solved for g of x. So I get 2g of x equals 6x plus 4, and divide everything by 2. So g of x equals 3x plus 2. Okay? And I'm going to even write down the word easy. I don't like to write word easy too much. But that's pretty easy. So think about it. Let's kind of just go back here. It says, what am I plugging into f of x to get 6x minus 2? So what am I plugging into f of x to get 6x minus 2? And that's kind of how you do that one. All right? That's not bad. Now, this is a more challenging one. So, again, this one's more complicated. So we have g of x is equal to x minus 4. But now I'm going to say f of g of x is equal to 2x plus 6. This is somewhat brutal. Okay? Because now what you're doing, well, the question here, of course, is what is f of x? All right? And before, it was easy to say, hey, well, what am I plugging into, into f of x to get 2x plus 6? But now I'm saying I want to know what function I'm going to plug g of x into to give me 2x plus 6. So we need to plug in g of x into something to get, which is your f of x, of course, to get 2x plus 6. Alright? So this is the deal, mathematically. I'm going to plug in an x minus 4 to get 2x plus 6. And I want to know, what am I really plugging into? Well, this is the deal. You got to kind of start with the variable first. Okay, the reason you start with the variable first, math fans, is because in order to get the from x to 2x, you can't just add and subtract things. Okay, especially because we're working with a number. What you need to do is you need to multiply. All right, so I'm going to say we need to have 2x. Alright, so basically what we're going to do is we're going to say 2 times x minus 4, because that's going to give us 2x. That's going to give us 2x minus 8. Okay, so far. But again, remember, we need to get it to be 2x plus 6. So now what do you do? The second thing is we're going to deal with the constant. And you're going to say, oh, negative 8 plus what is going to give you our value that we need, 6. And, I mean, you can call that another variable. Just call it y just to solve it, right? And we add 8 to both sides, and we have y equals 14. So what we need to do is, that 14 is what our answer is. That's what we need to add to that. So it's going to be f of x is equal to 2x plus 14. Okay, that kind of compensates for that. That's the deal, is we have this minus 8, and we need to figure out, hey, how do I get that minus 8 to give me the 6? Well, I add 14 to it. So this is my f of x. All right, now how do you check it? Guys, it's really easy to check just to see if it works. Okay, just do f of g of x. So we're going to plug g of x into that. So f of g of x, I'm going to plug g of x in that. So 2 times x minus 4 plus 14. So you got 2x minus 8 plus 14, or 2x plus 6. Okay, and there we go. That's what our answer is, 2x plus 6. Okay, so it's just a good way to check it. All right. All right, so that's a little bit more in composite functions. Let's do some problems now with exponential functions. So again, this is kind of all review for you guys. You guys should really remember all this stuff from 328, working with exponential functions. So let's write that out here. Okay, an exponential function is basically y equals a to the x. Okay, so now let's look at some of the functions and graphs, some basic ones. Okay, here's your first one. I'm just going to say y equals 2 to the x. Okay, and again, you can, if you're not sure, you can plot a couple points, but we're just, we know that like 2 to the 0 power is 1, and 2 to the second, so right as it gets bigger and bigger and bigger, it's going to grow exponentially, as they call it. Okay, so this is what the graph is going to look like that. Okay, second graph, y equals negative 2 to the x. So we're going to try and fit 6 graphs on here. So negative 2 to the x is just, it's growing, but it's growing in a negative direction. So it looks like that. Okay, the third one is y is equal to 2 to the x plus 3. Well, if you guys remember from algebra 2, that's going to actually shift it to the left. So it's going to shift it like that to the left. Because what's going on is it's getting bigger earlier, right? If I put a 0 in there, it used to be 2 to the 0 is 1, but now if I put a 0 in there, it's really 8 already, so it's getting bigger faster. So basically you have a shift to the left. Okay? And let's try another one. How about y equals 2 to the negative x? Well, this is called, again, by the way, all these guys are growth. And this is growth, even though it's in the negative direction. And this is growth. So this guy right here, as x gets bigger, y gets smaller. So this guy is going to look like this. And this is called exponential decay. Okay, and fifth one, we have y equals negative 2 to the negative x. Yeah, that's actually pretty easy. It's very similar to the one number 4, except it's not, it's still exponential decay, but it's decaying in the negative direction. Okay, so it's going to look like this. So this is also decay. And then the last one, how about y equals 2 to the x minus 3. Well, what is that doing? That's actually just moving up and down. That's just a shift, and that's a vertical shift going down. Okay, that's all it does. So this is, again, this is a growth problem. but it's shifting it down 3 units. Okay, that's pretty easy. Let's talk about one of these functions now. Just kind of analyze one function. So we're going to do y equals 2 to the x minus 4. Okay, and I want to talk about our domain and range, and I want to talk about x-intercepts and y-intercepts. You got to know this stuff, so that's why I'm doing a couple examples here, math fans. All right. So let's talk about our range first. Okay, range is values of y, acceptable values of y, and you guys need to realize that you're kind of looking to say, I know something minus 4, but we're kind of looking to say, what can that value be? Well, obviously, as it gets bigger and bigger and bigger, y gets bigger and bigger and bigger, right? So it's going to be something to infinity. Well, what's the smallest value that can be? Okay, so think about it. 2 to the 0 is net 1, and 2 to the negative 1 is net 1/2, and 2 to the negative 2 is 1/4, and 1/8, 1/16. So really, it never goes to 0, right? But it gets really, really, really close to 0. It never goes negative. So what that is it gets close to 0. But not quite. So when you say not quite, that just means we're going to use a parenthesis. Okay, so 0 minus 4 is negative 4 to infinity. Of course, the infinity is always has a parenthesis. And that is what my range is, negative 4 to infinity. Okay, now the domain is actually easy for these problems, math fans. And the reason it's easy is because can x be any value? Right? There's no restriction on what x can be. So the domain is between negative infinity and positive infinity. Alright, that's actually pretty easy. Let's talk about our x-intercept. Well, how do you find an x-intercept? You set y equals 0. So let's do that. 2 to the x minus 4 equals 0. So 2 to the x equals 4. And now what you can do is you can take the log of both sides, or you can say 2 to what power is 4? Okay, x equals 2. That's the answer to that. All right, so my x-intercept, and give me a coordinate because that's truly what it is, it's 2, 0. All right, let's find our y-intercept. How do you find the y-intercept? That's actually easier. You set x equal to 0. So let's do that. Y is equal to 2 to the 0 minus 4. So it's anything to 0 power is 1, don't forget that. Minus 4 is negative 3. So we get 0, negative 3. That's your y-intercept. Okay? Pretty easy. All right, let's do one that's a little more complicated. Y equals negative 2 to the negative x plus 7. All right, so let's look at our range. The range is going to be, again, what is the smallest value this can be? Okay, well, I guess what I'm saying is, do you guys agree? Well, let's even ignore the negative for now. 2 to the negative x, that is getting closer and closer and closer to 0, right? So that's closer and closer and closer to 0, plus 7 is 7. So one part of that range is 7. But this guy has a negative with it. So as this number gets bigger, then with that negative it's going to be smaller and smaller and smaller. All right? So that means it's going to be more negative. So in other words, the reason I'm talking about all that is because this is going to be negative infinity to 7. Okay? If that negative was not there, then the range would be 7 to infinity, because the number would keep growing. Okay? Does that make sense? I hope. All right, so that's my range, negative infinity to 7. And the domain, well, that's kind of easy. Again, domain is easy with these kind of problems because it's just negative infinity, positive infinity. There's no restriction for the domain. All right? And our y-intercept is easy because you set x to 0. So it's y is equal to, it's 2 to the 0 power is 1, or it's negative 1 because there's negative plus 7. So it's 6. So the y-intercept is 0, 6. Okay? The x-intercept is a little tougher. Well, the reason the x-intercept is tougher is because it's not a nice number. That 7 is not a nice number. So remember, set y to 0. So we're going to get negative 2 to the negative x plus 7 equals 0. That is really key here. And I'm going to show you two different ways to do it. One is with logs, so let's do that first. As opposed to subtracting 7, I'm going to add 2 to the negative x. So I really get 2 to the negative x equals 7. I'm going to take the log of both sides. Remember that exponent comes down in the front. So it's negative x log of 2 equals log of 7. Divide by negative log of 2. So x comes out to be negative, I'll put in a quarter right away here, negative 2.8074, 0. That's the x-intercept. Okay? Okay, so now what we can do is we can actually use our TI to figure out the solution. Of course, these are x-intercepts, same thing as finding your roots. So we'll bring up virtual TI here. And let's plug in our equation. Y equals negative 2 raised to the... I'm going to put this in parentheses. I like putting stuff in parentheses because then I know it's the only thing raised to the negative x power. And then plus 7. Okay. And I hit enter 2. And I'm going to do zoom 6. Gives us a good graph. Okay, and then let's find a second, calculate our 0. And let's go to the left bound. Oops, went a little too far. It's okay. And then our right bound, go to the other side of that. Doesn't have to be too far, as long as it's a little bit. Enter, and then guess, enter again. Ah, look at that, man. Negative 2.8074. Okay, so that's what we found it. Let me go back to this guy right here. Right, x for the TI, you got the same thing. Negative 2.8074. Okay, so make sure you know how to do on both manually using logs and with the text instrument calculator. Okay, you gotta know how to do that. And I want to see keystrokes. Okay, so you label all the keystrokes that you use to solve this. All right, let's try another one here. Alright, so y equals 2e to the x minus 4. And guys, remember that e to the x function, that's an exponential function. Okay, and this is called base e. Alright, and e is equal to 2.718. Okay, and just to talk a little bit about it, it's a constant used to model growth, exponential growth, and decay, and continuously compounded interest. Okay? All right, it's not too bad. All right. So let's just talk about how to find. So to find a value of e, basically what you do is you have f of x is equal to 1 plus 1 over x to the x power. And we haven't talked about this yet, which is a limit, but x is going to go towards infinity. So this is the deal. When I say x approaches infinity, you're going to plug in a really large number for x, just for now. Okay, so I'm going to do 1 plus 1 over going to plug 1,000,000 in. And that's the 1,000,000th power. And if I do that, I get 2.718280469. And if I actually type in on my calculator, I do second ln, which is the same thing as doing e, and you raise that to the first power. That's e to the first power, it's just e. And you get 2.718281828. Okay, so you can see these are very close. Okay, and obviously as the bigger number you get, the closer it even gets. All right, so anyway, talked a lot about e. Let's graph y equals 2e to the x minus 4. Okay, couple things. Let's get our domain. You guys agree the domain can be anything, right? Because it's kind of the same deal as saying, 2 to that power, right? So it's going to be negative infinity to infinity, and then our range. Well, what's happening when that value, right, especially that x value gets negative? Don't you agree? It's 1 over that value, so it's getting really, really, really close to 0. And then minus 4. So it's going to be not including that, though, because it's getting close to 0. So it's negative 4 to infinity, because it's positive value. So you're going up and up and up. All right? And the y-intercept, again, is really, really easy. You just plug in x for 0. And the 0 is 1. 2 times 1 is 2. 2 minus 4 is negative 2. So y equals negative 2. So it's going to be 0, negative 2. That's your y-intercept. Okay. And then your x-intercept, again, a little more challenging, but let's just use our knowledge. 2e to the x minus 4 equals 0. So this is my x-intercept. And I'm going to add 4, so I get 2e to the x equals 4 divided by 2. E to the x equals 2. How do you solve that? Do you remember, you take the natural log of both sides. That's the same thing as taking log base e. And so that goes into the front. So it's x ln of e equals ln of 2. Now you don't need to divide by ln of e, math fans, because ln of e, if you type ln of e in your calculator, you're taking the natural log of e, which is 1. That's important. That's equal to 1. So really you're just saying x equals ln of 2. Okay, and ln of 2 is 0.6931. So it's 0.6931, comma 0. All right, and then let's look at the TI here. Okay, I'm going to put y equals 2 second natural log, so 2e to the x. Don't forget to close parentheses, math fans. If you don't close parentheses, you're going to do raise the e to the x minus 4, but you want to do e to the x and then subtract 4. So then we're going to do minus 4. Okay, and we can do zoom 6, and there's the graph, and then of course I want to find my x-intercept. So second, calculate 0, and we're to the left of it. That's good. Hit enter, and then to the right of it, hit enter again for guess, and it's 0.6931. Okay, which is exactly what we got. 0.6931 comma 0. Okay, so you get the exact same answer. Just be careful, you're with your calculator and even with taking logs. All right. I'll be very specific which way I want you to do it. So make sure you either give me keystrokes or you give me all the work. Don't just give me an answer. If you give me an answer, you really are not going to get any credit for it. Okay, you need to show me the work behind it. All right. Let's do a couple more exponential problems here, math fans. Okay, if I give you guys 1 over 81 to the 3x minus 4, and let's just say I want the base to be 3. Okay, how can you rewrite? So I need to rewrite. So it's 3 to some power as an equivalent to that. 3 to some power. And I need to figure out what that power is. Okay, so this is the deal. If you guys remember, 1 over 81, isn't that the same thing as saying 81 to the negative 1 power? Because I'm trying to get that to look like a 3, right? So it's 81 to the negative 1 power, and then what is 81? Isn't that what? 3 to what power? 3 to the 4th power? Okay, so it's really, that's equal to 3 to the 4th power to the negative 1. Okay, so again, I'm writing all that in terms of 3. So isn't that equal just to 3 to the negative 4th power? So now I've just rewritten 1 over 81. That's 1 over 81 to 3 to the negative 4th power. But now I need to raise that to the 3x minus 4. And what do you do with the power? You multiply it. So it's 3 to the negative 12x plus 16. And that's actually your final answer. Okay. Alright, let's try another one here. 4 to the x power is equal to 1.2. Well, you can either use logs or TI, so let's do both again. I take the log of both sides. So it's x log of 4 equals log of 1.2. Divide by log of 4. So x comes out to be 0.1315. Pretty easy. Okay, let's check out our TI. 4 to the x is equal to 1.2. So I need to move this over, right? I need to say, it doesn't matter which one I move over, so I'm going to move over the 1.2. 4 to the x minus 1.2 equals 0. So really I'm graphing that, and then I'm saying find out where that's equal to 0. Okay, and that's going to be my x-intercept. So that's how you use your graphing calculator here. Okay, so let's do that. 4 to the x minus 1.2. Now notice what's going on. It's going to do that 4 to the x, and then it's going to subtract 1.2, which is exactly what I want to do. So zoom 6, and then second, calculate 0, left bound, right bound, enter 1.3 or 0.1315. 0.1315. Hey, look at that. Sweet. Same value. All right. Okay, so another example here. We're going to say solve. And it's e to the 2x equals 105. Sweet, 105. Okay, so let's take the natural log of both sides. Oops. Take the natural log of both sides, and so we get 2x ln of e equals ln of 105. Divide by 2, because right, doesn't it go to 1? Ln of e is 1. Divide by 2. So it's x equals 2.3270. Again, try on your calculator and figure it out. And so the same thing, let's graph this. It's y is equal to e to the 2x minus 105. Right? And then I'm going to just set that equal to 0. And then use my graphing calculator. Second e to the 2x, close parenthesis, minus 105. And we're going to do zoom. And let's see, is zoom 6 going to work? Zoom 6. No. So we're going to do is zoom, because that 105 is weird, zoom fit. Alright, and that kind of worked. You can kind of see a little bit there. Alright, and so what we're going to do is we're going to do second, calculate 0. And left bound. Just kind of clicking that number a little bit. I think we went way too far. I'm looking for, if you look at the y value, see how the y value is changing? See how it's negative there? I just know it's below the for the left bound. So I can hit enter, and then I can move to So it's positive. And I know it's positive right there. And I can hit enter. So there it is. 2.3270. Okay, go back to this guy again here. Yeah, right, 2.3270. Okay, that's easy. All right, so here's my last example with the using logs and everything. How do I have 4 to the x power plus 2x equals 5? How do you solve that using logs? That's actually pretty challenging. So really, if you're given a problem like this, you're going to use your TI. All right, it just makes so much sense to use your TI. So what I'm going to do is I'm going to say y is equal to 4 to the x plus 2x minus 5. All right, I'm going to move the 5 over, and then it's equal to 0. So I'm saying, well, where is that equal to 0? Well, again, that's going to be our root or our 0 value, okay, on the calculator. So let's graph that one. That one's challenging. You can't do that one so easily by hand. 4 to the x power plus 2x, we're okay with parentheses here, minus 5. And then we're going to do zoom 6, zoom standard. Ah, there we go. So second, calculate 0. And it's already flashing the left side. And then right side, it's flashing. Hit enter. And the answer is 0.8578. So it is 0.8578. That's the answer to that. Okay, and you can check it, right? You know, I mean, obviously it's a little bit of a rounding error. Okay, and then we can test this on our calculator just by kind of typing things in a little bit. Okay, and if you don't have time to do it, you don't do it. But if you have time, plug it in. So we're going to do 4 raised to the 0.8578 plus 2 times 0.8578. That should be really close to 5. Yep, there it is, man. 4.999. Okay, really close to 5. So we definitely did the right work here. Okay. All right, math fans. The last part of this lesson, it's kind of a lengthy lesson, but the last part I typed up for you because it's just too many words when you do any applications, and we actually kind of did this together. So I'm just going to kind of talk through this. You have this all in front of you, but if you don't want to listen to me, then just look at the note sheet, and it's pretty easy. All right. We are going to use some of the exponential functions here for population growth. After 1 year, the new population is equal to the starting population, and that's 1 plus the growth rate. Okay. So in other words, I'll give you an example down here, but if whatever the population is, you're going to multiply that by, let's say I'm increasing it by 5% every year. You're going to take whatever the current is, and you're going to multiply by 1.05. Because you multiply just by 0.05, you get 5% of the population. You want 5% added to that population. Okay, and so that's the same thing. After 2 years, it's one first year population, and then another times the growth rate. So basically, I'm just kind of developing the formula. And what you have is it says, so after 2 years, remember the exponential growth rate is okay, so after 2 years, if you remember, the exponential growth rate is then that equation. All right, and that's because I'm doing 1 plus the growth rate, and then the next year it's times that again, the growth rate times that again, that times that again. That's where I get t. Okay, raised to the t power. So that's your population growth formula. Okay, a is equal to p 1 plus r to the t power, and I even put where p is equal to the starting population, r is the growth rate, and t is the number of years. Here, an example is the current population of Conant, 2,800. Population increases by 2.53% each year. When will the population be 3,500? Okay, so here it is. Set it up nicely. 3,500 equals that. I even said use either property logs or your TI-84. If I use my TI-84, I got, I graphed and used the root key or the 0 key. I got 8.93 years. All right. Interest is the same formula. It means the same thing. P is called the principal, which is how much money you invested initially, and the amount is how much you have after so many years, and R is your interest rate. Please remember to make that rate, that R, as a decimal. Okay, don't put 5% and put a 5 in there. That's like saying 500%. That's brutal. Okay, so how long? Now this is a good question. How long until you can double your money when the interest rate is 6.15% interest? And some of you guys are saying, well, Mr. Curvis, I don't understand. How do you know what your initial amount is and your final amount if it's doubling your money? Well, I don't need to know that. Okay, even put it on there. You don't really need to know the starting amount. You just make A equal 2 and P is equal to 1. You're doubling your money. Okay, because when you double, I can make that $2,000 and $1,000. When you divide it out, you're still going to get, divide out the same thing, right? You're going to get, 2,000 equals 1,000. You're going to get 2 on that one side. Anyway, I'm going to use my graphing calculator, and it comes out to be 11.614 years. And I'm if I did a little bit different interest rate, 6 or 5.15, you can see it's going to take, right here, it's going to take a little bit more time, 13.8. So, we'll talk a little about this later, but it's important to have good interest rates, okay, to help you make money. Compounding continuously, that is using your nice little formula. You probably learned that before, but A equals PE to the RT, or PERT. Okay, so compounding continuously means you are compounding every second. You keep on reinvesting, because what you're doing is you're reinvesting money, and then you're making interest on that money you just reinvested, and then you make more money, and you take that and put it back in, and you make, keep reinvesting. Okay, and so if you do that, you're going to use it's kind of the same concept. 2 equals 1 e to the 0.0615 t. Again, you can take the natural log of both sides, or use your graphing calculator, and if you notice, you get t is equal to 11.271 versus compounding yearly 11.614. Okay, and obviously the lower the number of years, the better, because you're making money faster. All right, so more compounding is better. The ultimate is compounding continuously. Compounding yearly, that's pretty cheesy. Compounding monthly is what a lot of banks do, but it all depends on your bank. All right, last one, Half-Life. It's definitely a good video game out there, but Half-Life is also the time required to reduce something by half. All right, so the half-life of plutonium-239 used for weapons and energy is 24,000 years. If you start out with 1 pound of Pu, Purdue University, plutonium-239, how long until there is only 1 ounce left? So we're going to use this half-life equation, and if it's a little small, but the end amount is equal to the initial amount, and that 1/2 is your rate. So it's half-life, half of it, okay, raised to the time divided by the half-life time. So in other words, what I use for this one, I have, if I plug in my calculator, y1 equals 16. That's I'm trying to find out my ending value. And 16 ounces, because you got to keep units the same, times 1/2 to the x over 24,000 years. All right? And of course then it's minus 1 because that's your ending value. All right? So that I hope that makes sense. And this is because you're going from 16 ounces to 1 ounce. So 16 ounces to 1 ounce. I just solved for y there. All right, and what I did is when you do this problem, you want to set the window to an extreme value to see the graph. All right, and sometimes it's kind of difficult to see that window. Sometimes you just have to keep expanding it and expanding and expanding it to actually see what the graph is going to look like. And if you do that, then your answer is going to come out to be 96,000 years. All right, so try that on your calculator, but you just kind of expand your window to see what things look like, and you should be good to go. All right, it was kind of a long lesson, but covered a lot of stuff, and just make sure you know how to use logs. All right, that's it, math fans. Have a nice day. Adios. Goodbye.